Okay, so let us wait for a few minutes. So if anyone more joins, and then we will start the today's session. Okay, so today we will be having our session on the topic of. So we'll talk mainly about the physical layer and what are the protocols that are used to resolve or data sending between the physical layer, and what is LAN, VLAN, and wireless LANs. So overview of the today's lecture, we'll be covering these topics. And before starting for today's lecture, we'll first cover the previous week's assignment solutions. And okay, I'll share the assignment, and then you all have to make a quick answers to the question, and then we can further proceed with the today's lecture. So the first question is, what is the primary function of the data link layer in the OSI model? As you can see here, you can respond in the chat. So I would request everyone to just answer the questions, and accordingly we'll share the discussion about the answers. Okay, so the answer to the question is D. To manage the primary function of data link layer in the OSI model is to manage the yes, is to manage the physical access to the physical network medium. The next question is which is not one of the LLC services. So LLC, as you remember, is a part of the data link layer. There are two parts. One is the LLC and another one is the MAC. So which of them is not a part of LLC services? So everyone, please answer to the questions. And if you have any doubt, and then we can have a discussion over the questions. If I think this assignment has already been solved by all of you guys, so it will be good if you have a interaction and give responses. Okay, so yeah, the correct answer is C. That is, logical link control sublayer provides services such as connection mode service, acknowledged connectionless service, and unacknowledged connectionless service. However, intermediate switching service is not one of the defined services of LLC services. Okay, so next question is every station connected to Ethernet network is provided a 6-bit byte physical address by How connectionless? It is a part of service that LLC provides, like a connectionless service uh, an acknowledged connectionless service and acknowledged connectionless service as well as connection mode service. In the connectionless service, you need not to have a connectionless means that you do not need to have a setup of the connection. Like there need not to be a wired connection or there need not to be a setup of that connection beforehand. So connectionless also you can provide the service from the LLC layer. So the answer to this question is B, that is network interface card. Then next question is when two or more bits in a data unit has been changed during the transmission, the error is called a random error, burst error, inverted error, or double error. Yeah, so the answer is B, that is burst error, occurs when two or more bits in a data unit have been changed during transmission, and it is often caused by noise or interference affecting consecutive bits. So next question is which sublayer of the data link layer performs data link functions that depend upon the medium? So here medium is involved in which sublayer? Yeah, so the sublayer of the data link layer that depends upon the medium is MAC layer, that is media access control. which performs data link functions that depend on the medium, such as controlling access to the network medium and addressing frames for transmission. Next question is, in carrier sensing sense multiple access or collision detections, that is CSMA-CD, the sending station must detect collision, signal, sense, or station. Yeah, so the answer to this question is A, that is collision, not C, that is sense. So in CSMA-CD, the sending station must detect collisions on the network before retransmitting its data to avoid data corruption or improved network efficiency. So in go back and ARQ, if the sequence number is represented by 4 bits, the sender and the receiver window size should be what? Sequence number is defined by 4 bits. So what is the size of the sender and the receiver window? Mm. Yes, that's right. It's 15, comma 1. That means the sender window must be less than 2 to the power m, and the receiver window is always 1 in go back and ARQ. So it is 2 to the power 4 minus 1, that is 15. That is the sender window, and go in receiver window is always 1. So next is in go back and ARQ, if the window size is 63, what is the range of sequence numbers? Yes, so the correct answer is C, that is 0 to 63. As it is also having a similar explanation that the window size sequence number are from 0 to the window size -1, and the window size is 63, so sequence number will range from 0 to 63. So in a network using CSMA-CD has bandwidth of 10 Mbps. If the maximum propagation time, including the delays in the devices and ignoring the time needed to send a jamming signal, as we see later, is 25.6 microsecond, what is the minimum size of the frame? Yeah, so the correct answer is D, that is 64 bytes. So here is the explanation that the minimum frame transmission time, that is TFR, is 2 times the transmission uh, propagation time. Okay, that is 2 into 25.6. This is 2 into 25.6, which is 51.2 microseconds. This means in the worst case, a station need to transmit for a period of this much seconds to detect the collision. So the minimum size of the frame is 10 Mbps into 51.2 microseconds, that is 512 bits or 64 bytes. This is actually the minimum size of the frame for standard Ethernet also. So I hope everyone is clear with this question, no doubts. So when an acknowledgement is lost during go back and ARQ, the receiver transmits the acknowledgement after a timeout. Is it a true or a false? Yeah, so the answer to this is false, that it is not true that it retransmit after a timeout. Okay, so this was the previous week's assignment that we have discussed. If anyone has any doubt, you can ask. Otherwise, we'll proceed with the today's lecture. False is that the receiver does not send an acknowledgement in go back and ARQ. So it automatically retransmits after a certain timeout. Acknowledgement is not sent in go back and ARQ. Okay. Yeah, so in this lecture, we will discuss certain protocols about the physical layer and what is the LAN and VLAN and some other terms. So first protocol that we will be discussing is the address resolution protocol. I'll just give a broader overview of this week and then we can discuss the assignment of this week as well. Then what is address resolution protocol? So whenever two machines on a given network wants to communicate with each other, they only know each other's physical network. They only know each other's IP address from that is they receive it from the network layer. So, but how can they communicate if they do not know the physical address, network address? So for that purpose, we have the ARP, that is Address Resolution Protocol, which serves for mapping from higher level IP address into a lower level MAC address. So this is how it is done, that we have multiple machines with different IPs and different MAC address. So ARP response, a request is broadcast to all the machines with this IP. So we want to find the MAC address of this IP. So we find that this IP is there in the broadcast request, and then we have the corresponding MAC address to that particular IP. And then as a response of ARP response, that MAC address is sent to the sender. So this is what the ARP does. It has the logical address, that is the IP address, and it converts it into the physical address. And then there is the RARP, which has the physical address. When we have the physical address and we want the IP address corresponding to that machine. So where are ARP and RARP positioned in TCP/IP protocol suites? So they are positioned in parallel with the network layer, in between the network layer and the data link layer. So this is the network layer we have, and beneath that it is the data link layer. Then the ARP and RARP is placed in between the network layer as well as the data link layer. So what is the operation? As I mentioned, like system A is looking for an IP address, physical address of node with IP address 141.23.56.23. So it sends a ARP request, and ARP request is always sent as a broadcast message to all the other systems. Then that request is sent to 1, 2, 3, 4, all the systems in the network. Finally, when the system retrieves the physical address, then it gives the reply back to the system A as a unicast way of sending the message. So ARP reply is sent as a unicast message. So ARP request is a broadcast and ARP reply is a unicast. So this is the packet or type of headers that are involved in ARP protocol. Here we have the hardware type and the protocol type, then hardware length and protocol length. So here normally the hardware type uses Ethernet. So one we have the sender's address, hardware address, and another is a sender protocol address, that is the IP address. And then we want the target hardware address, that what will be the hardware address, which is not present in the at the time of request. And then we have the hardware protocol address, that is the IP address, which is present at the time of request. So there are four cases in ARP protocol. Then first is that sending a host has a packet to send to another host on the same network, similar host on the same network. Then a host wants to send a packet to another host, but on a different network. It must first be delivered to a router then. So first to router and then to that particular network. Then there is other case where a router receives a packet to be sent to a host on the another network. And then there is a router receives a packet to be sent to a host on the same network. So this is the example which we are considering, that a host with IP address 130.23.43.20 and physical address B2 dot 34.55.10.22.10 has a packet to send to another host with the given IP address and the physical address which is not known at the to the first host. So the two hosts are on the same Ethernet network. So show the ARP request and the reply packets encapsulated in the Ethernet frame. So this is how it is shown. This is the request packet. This is the ARP request packet, and here is the data. In the data, we have this ARP, all the headers of the ARP. Here, the header for the target MAC address is set to 0, and this ARP request is sent as a broadcast message. Then when we receive that particular MAC address, it is sent as a reply and the order shuffles. Here is the sender's MAC address and this becomes the sender because it sends a reply from B to A. Then the sender's address, then the receiver's MAC address and IP address. So now we have a term called proxy ARP. A proxy ARP is running in a router can respond to an ARP request for any of it or of its protogees. So the proxy ARP replies with its own MAC address. When the packet arrives, the router delivers it to the appropriate host thereafter. So we have the request, the proxy ARP routers replies to the ARP request received from this destination with multiple destinations. So it acts as a proxy ARP or in a router which contains the ARP request for multiple systems that are present in that particular subnetwork. So proxy ARP is also called Prometheus ARP or ARP hack and is a technique to use to map to a single IP network prefix into two or more physical addresses. So using the same network address space for more than one physical address. So here, the assumption is that there are two networks A and B connected by a router that runs a proxy ARP. So using this proxy ARP, R can use the same network ID for both the networks. There are certain software models used for ARP protocol. One is the cache table, which can store multiple information about the multiple sources, destination, the port, the router, and etc. Then there is queue, which stores multiple ARP requests. Then we have the output module, an input module, and cache control module. So we'll discuss a few points about the ARP cache table. So here, if ARP just resolved an IP address, so there are chances are a few moments later that there is a request to resolve the same IP address. So when ARP returns a MAC address, it is placed in the cache so that again it need not to go through the whole process of going to the machine and finding out its MAC address. So when the next request comes in for the same IP address, it first looks into the cache, and if that conversion is present in the cache, then it need not to go to the whole process. So what are the table contents of the cache table? One is the queue number, which queues the ARP request is sitting in. Then attempts, how many times you have tried to resolve this address. And timeout, how long until this address is tossed out, need the room in cache. I mean, if there is a address and it is not required for more than a certain amount of time, then it is tossed out of the cache rows or cache table. Then we have the hardware address, which is the destination hardware address, and protocol address, which is the destination IP address. So the working of the cache table is that the output module waits for the IP packet with a request. Then it checks the cache for an existing entry. So if the entry is found and the state is resolved, we already have this MAC address. So if entry is found and the state is pending, then the packet waits until the destination had the address found with it. So this is a sort of cache table, as you can see here, with the state, whether the request is this we said, whether the request is resolved or it is pending. Then we have the queue, what is the number of queue of the request, then how many attempts are made for that particular IP address, then what is the timeout of that particular request, and the protocol address, which is the IP address of the destination, and the hardware, which is the MAC address of that destination. Have a look at this cache table if you have any query. Okay, I hope it's clear. So, okay, what is queue? So queue is basically which queue the ARP request is sitting in. There are multiple number of queues, 1 to n number of queues. So in which queue that ARP request is coming in, it defines the queue number. So I'll show you with the example that for example, from the given table that this is the table. And then we have the ARP output module receives the IP datagram from the IP layer with the destination address given as 114.5.7.89. It checks the cache table. See, 114.5. This is the entry we can see here. Wait. This is the entry 114. Okay. So it checks, it finds that an entry exists for this destination with the, what is the state? The state is resolved. So it is resolved. That means it has the hardware address of that particular entry. So if the hardware address is there, and then it sends the packet and the address to the data link layer for transmission. So the cache table remains the same as it is. Till now, I think it's clear to everyone. This is how we see the cache table. If at any point, if you have any query, you can raise the hands. Then 20 seconds later, the ARP output module receives another IP datagram from the IP layer with the destination address 116.1.7.22. You can check 116.1.7.22. You cannot find anywhere here. Okay. So it checks the cache table and does not find this destination in the table. So the module adds an entry to the table with the state pending because it is not yet has received the address of the hardware, and then the attempt value to be 1. So here you can see it is new entry is created with the pending value with the attempt 1 in a queue number 23. It then sends an ARP request to the data link layer for this destination. So this new cache table is shown here where the request is sent. So they tell then 15 seconds later, the ARP input module receives an ARP packet with the target protocol IP address, that is 188.11.8.71. The module checks the table and finds this address. As you can see here, 188.11. This and finds, and its state is pending. Okay. Okay, it receives an ARP packet. So it receives the ARP packet, not the request, but the ARP input module receives the packet back, and then it input the entry for the that resolve. It changes the state of that entry to resolve and set the timeout value to 900. The module then adds the target hardware address to the entry. So earlier we had the IP datagram from coming and with the destination address, but now we had the ARP input receives the ARP packet. So now it accesses Q18 and sends all the packet in this queue one by one to the data link layer. And this is the new table. This row is added and the address corresponding to this is also added. Then 25 seconds later, the cache control module updates every entry. The timeout value for the first 3 resolved entries are decremented by 60. So the timeout value for the last resolved entry is decremented by 25. The state of the next to last entries changed to free because the timeout is 0. So here it was earlier 60, but it is now timed out. So it is 0. So it is now for each of the 3 pending entries, the value is attempt field is incremented by 1. So this entry is now removed. This is a free area. So I think everybody is clear with the ARP and ARP cache, how it is done. So it was quite easy to understand. Okay. Then we have another protocol, which is RARP, which is the reverse that finds the logical address for a machine that only knows its physical address. This is often encountered on a thin client workstations where no disk. So when machine is booted, it needs to know the IP address of that machine. So RARP requests are broadcast and the replies are unicast in the similar manner of ARP. So if a thin client workstation needs to know its IP address, it probably also needs to know its subnet mask, router address, DNS address, etc. So we need something more than RARP, that is BootP and DHCP, which have replaced the RARP, because RARP just provided the IP address, but we also probably need the subnet mask, router address, and DNS address. So here the RARP request is broadcast and the reply is unicast. So the RARP packet format is very much similar to ARP. In this only the sender protocol address is not there. And however, the sender's hardware address is there and the target hardware and protocol address we have. So accordingly, we get to know about the sender's IP address. So it is also encapsulated in the field of data. So now we'll discuss the BOOTP protocol. So Bootstrap protocol allows a host to configure itself dynamically at the boot time. This protocol provides three services. One is IP address assignment, then is detection of the IP address of the serving machine, then the name of a file to be loaded and executed by the client machine. So BOOTP packet is assumed to never fragment into pieces or into fragments. BOOTP uses two well-defined port numbers. One is UDP port number 67 for the server and UDP port number 68, which is used as a BOOTP client. So what is the process? That the BOOTP client broadcasts a single packet called the boot request packet containing the client's MAC address. Then the client waits for a response from the server. Like this is a client. It sends a boot request as a broadcast message to the server to different machines, and then it receives a response from the server. So if not received within a specific interval, the client retransmits the request. So the server responds with a boot reply packet to the client, and then client knows the IP address of its machine. So BOOTP is an alternative to RARP, which operates at the data link layer for LAN only. So BOOTP is it is a UDP or IP-based configuration protocol, which provides more configuration information and allows dynamic configuration for entire IP network. So BOOTP and its extension becomes the basis of DHCP protocol. So this is the packet format of BOOTP with different number of headers, as you can see here. Then the operation code of BOOTP is 8 bits with value 1 as a boot request and value 2 as a boot reply. Then we have the hardware type of 8 bits, value 1 as Ethernet, 2 as experimental Ethernet, 15 as frame relay, and value 19 as ATM. So this is the boot operation that the client sends the request to the server and gets a reply from the server. So this is the type of request that is sent with the source port and the destination port, and the source address and all the destination address are set to 1, that is broadcast, and the source address has 0, that is it doesn't know its address. Then it receives as the destination port and source port, and then the source address, which is the server unicast reply to the client, and the destination address, which are all ones, or client unicast address. It is a kind of similar thing to RARP, but just for the LANs. Now we have DHCP, which is Dynamic Host Control Protocol, which is used to centrally allocate and manage TCP/IP configurations for the client node. It allows us to define pools of IP addresses, which are then allocated to client computers by the servers. So these pools of addresses are called scopes. And not only are these addresses handed out, so also are the related configuration settings like the subnet mask, default router, DNS server, etc. are also provided. So the DHCP packet is very much similar to the boot packet format. These were the protocols. If you have any doubt till here, you can ask now. Then we'll continue about the wireless LANs and the LAN. Yeah, so in the boot ARP, it is a similar thing, similar to RARP, and it only gets you the IP address of the machine. Okay. However, in the DHCP, there are scopes for subnet mask, default router, DNS server. These kinds of information are also present along with the IP address. Okay. So we'll proceed further. As you all know about the layer-wise connectivity, what are the connections and how do we know that there are multiple layers? Then the application is there, then the transport layer, which gets communicated by the gateway. Then we have the layer 3 switch or router with network to network interconnectivity. Then L2 switch or bridge for data link layer connectivity. And then hub or repeater for physical layer connectivity. So what is the repeater or hub? So it is used for connecting two segments of the LAN at the physical level. Okay. So it also enhances the strength of the signal, as we have also initially discussed. So it acts as a signal regenerator and it allows no filtering. And hub is a multi-port repeater. This is a single port, but hub is a multi-port repeater and it is a hierarchy of hubs. Then bridges are for connecting LANs. It is a present in separating collision domains, and MAC address are used for filtering traffic. And there are connected segments from it connects segments from a single network and same broadcast domain. So these are the broader ideas that we have already discussed earlier. So what is the bridge table? Say there is one LAN 1 and LAN 2 and the bridge with two ports, one port and two port. And then this bridge is connected with both of the LANs, but we do not have the address. We have multiple machines over one LAN and multiple machines over other. So we need to assign which machine has been allocated to which port of the bridge. So that port is done when there is a connection and the sending of data happens in between. So earlier the tables are empty. Then after A sends a frame to D, it gets to know A is connected at port 1. Then after E sends a frame to A, then it knows that E is connected to port 3 because the request is coming at port 3. If after B sends a frame to C, it knows that B is connected to port A. So this is how the bridge table is being populated or learns the information, which port is connected to which machine of the LAN. So however, in this case of propagating, there are a possibility of a loop problem where the case that station A sends a frame to station D. So here there are two bridges, bridge 1 and bridge 2 with the same port numbers. Then the two copies of the LAN of the frame are received on this LAN 2 at D point. Because from both the bridges, it is unable to resolve to which bridge to go. And again, both the bridges forward the same frame. Like if D wants to send a copy to A, then again both the bridges forward the same frame. So multiple frames are getting propagated from both the bridges. This leads to a problem of loop and enormous number of frames gets transferred. So how to handle a loop problem in transparent bridge? We do this using a spanning tree protocol. So I think all of you knows the spanning tree. That is the tree in which there is no multiple directional route from one node to the another. And also they follow the shortest route from one node to another. So they build up a spanning tree in between the nodes of one node to another through the bridges. And with the help of this spanning tree, they are able to handle the loop problem. So how to apply a spanning tree? I'll just give a broader idea. If you want to know the details, you can ask then. So every bridge has a unique ID. It selects the bridge with the smallest ID. Say with the smallest ID, here we first select bridge B1. Then this is called the root bridge. So mark one port of each bridge except the root bridge as the root port. So consider this B1 as the root bridge. We have considered apart from B1, all the other bridges consider one port at the as the root port. Say we have considered this as the root port, then for bridge this as a root port, then bridge this as a root port, and then bridge this as a root port. Okay. So root port is the port with least cost path from the bridge to the root bridge, and it is marked with 1 star. So you can see here, this is the from B4 to B1, this is the least cost path. So we mark this node as the root port with *1. Then this root as a root port, not this one because it's lengthy. Then this part as a root port. Then this part as a root port because it is shortest path. And this is how we mark the root port for each of the nodes. Then for each LAN, choose a designated bridge. Okay, a designated bridge has the least cost path between the LAN and the root bridge. So mark the corresponding port that connects the LAN to the designated bridge, the designated ports with the 2 star. So it is the least cost path between the LAN and the root bridge. So this is LAN 2. For LAN 2, we have the least path with this route as the to the root bridge. So this is also least path for LAN 1 and this is also least path for LAN 2. So this is marked as with two port as a designated port, and this is also marked as 2 port. Then this is the not the least path, just okay, and the root bridge we do not consider for everyone, only in the case of root bridge. Okay. Then mark the root port and the designated port as the forwarding port and block all the other ports. So all the other ports are then blocked. So here the blocking ports are this and this. Okay. So this is how spanning tree works, and because of this there will be no looping and only one path will be there. Okay. Now we'll talk a bit about VLANs. So VLANs are the virtual LANs which provide segmentation based on the broadcast domains. So VLANs logically segment switch network based on functions, project teams, or applications of the organization, regardless of the physical location or the connections to the network. So all workstations and server used by a particular work group share the same VLAN regardless of the physical connection or location. So VLANs are created to provide segmentation services traditionally provided by a physical router in LAN configuration. So VLANs address scalability, security, and network management. So there are two basic operations of VLAN, but it is statically and dynamically. So in statically operation, network administrator configured port by port. Each port is associated with a specific VLAN, and the network administrator is responsible for keying in the mapping between the ports and the VLANs. Then this is dynamically operating. The ports are able to dynamically work out their VLAN configuration and uses the software database of MAC address to VLAN mappings. So each switch port can be assigned to a different VLAN, and port assigned to the same VLAN share the broadcast. Ports that do not belong to the VLAN do not share these broadcasts. So the benefits of VLAN are that all systems attached to the same port must be in the same VLAN. And the key benefits is that they permit the network administrator to organize the LAN logically instead of physically. It helps an administrator to easily move workstations on the LAN, easily add workstations to the LAN, easily change the LAN configuration, easily control network traffic, and improve security. So without VLANs, there is no broadcast channel. There is an ARP request and no broadcast channel. And if we are with VLAN, then there is a broadcast channel. So then there is VLAN tagging, which is used when a link needs to carry traffic for more than one VLAN. For that purpose, we use the trunk link as the packets are received by the switch from any attached end station device. A unique packet identifier is added within each header. So this header information designates the VLAN membership of each packet. The packet is then forwarded to the appropriate switches or routers based on VLAN identifier and MAC addresses. Upon reaching the designated node, the VLAN ID is removed from the packet by the adjacent switch and forwarded to the attached device. Packet tagging provides a mechanism for controlling the flow of broadcast and application while not interfering with the network and applications. This is known as trunk link or VLAN trunking. So last topic we'll be discussing is the wireless LANs, which is for the proliferation of mobile devices, that is laptops, PDAs, and mobile phones, created an obvious application level demand for wireless local area network, and it is standardization by IEEE 802 committee. So the categories of wireless networks are the base stations, where all communications are done through an access point, and other nodes can be fixed or mobile. Then infrastructure wireless, where base station network is connected to the wired network. Then ad hoc wireless, where wireless nodes communicate directly with one another. Then MANET, where all ad hoc nodes are mobile. So this is the wireless LANs, where wireless networking is done with the base station. We have the base station, and these are the wireless networks, 1, 2, and 3. Then there is ad hoc network, where the wireless stations or the network communicate within each other without the base station. So as the IEEE 802 standard, PSS is the basic service set and AP is the access point. So this is the ad hoc network, BSS without an access point. So here are different stations which communicate with each other, but without a base station. And there is this infrastructure with there is a base station with the access point. Here in the stations communicate using this particular base station. So in the stack of data link layer and physical layer, this is how it is placed. So the physical layer, these are the standard protocols of IEEE that it uses. Then the MAC layer, it has the point control function and the distributed coordinate function. Then it is the PCF is the contention free service and DCF is the contention service. Then we have the LLC. So MAC sublayer protocol, in case of wireless LANs, it is a ceasing channel. It does not exist as in 802.3 wired Ethernet. So two additional problems are there because of the wireless communication, that is hidden terminal problem and exposed station problem. So to deal with these problems, 802.11 supports two modes of operation. One is DCF, that is distributed coordinate function, and PCF, point coordination function. All implements must support DCF, but PCF is optional. So what is hidden state and exposed state problem? In case of hidden station, A wants to send a message to B, but cannot hear that B is busy. So B is in the radio range of C. So A doesn't know that the B is busy, and so it wants to send a message to B. Then there is this exposed station problem that B wants to send to C, but mistakenly think that the transmission will fail because B is in the range of the radio A. But currently A is transmitting and B is not in the range of A. So it can, however, it is exposed to A, but it thinks that A has covered it. So it not transmits to C. So to solve the hidden terminal problem, what is hidden terminal problem? We have broadly seen. So here wireless stations have transmission ranges and not all stations within the radio range of each other. So simple CSMA will not work. So C transmits to B. If A senses the channel, it will not here cease transmission and falsely conclude that A can begin a transmission to B. So there will be a cross communication. Then in ex post station problem, it is an inverse problem that B wants to send to C and listens to the channel. But when B hears A's transmission, B falsely assumes that it cannot send to C, but it can send to C. So for that, we use distributed coordination function, that is DCF, which uses CSMA-CA collision avoidance protocol. Here it uses both physical and virtual carrier sensing. The two methods are supported based on MACA, that is multiple access with collision avoidance for wireless, with virtual carrier sensing, and one persistent physical carrier sensing. Then we have the PCF, point coordinated function, which uses a base station to poll other stations to see if they have frames to send. So if no collision occurs, the base station sends beacon frame periodically. So here base station can tell another station to sleep to save on batteries, and base station holds frame for sleeping station. So this is not a mandatory, it is an optional part. So here the coexistence, distributed and centralized control can coexist using inter-frame spacing. So SIFS, that is short IFS, is the time waited between packets in an ongoing dialogue. It is RTS, CTS, data, acknowledgement, and network next frame. So PIFS, PCF, IFS, when no SIFS response, base station can issue beacon or poll. So DIFS is when no PIFS and any station can attempt to acquire the channel. And EIFS is the low priority interval used to report bad or unknown frame. So this was the broader idea of what was covered in this week. If anyone has any queries, you can ask, and we will discuss this next assignment, which is floated as this week assignment. So we will be discussing the sample assignment based on it. Okay. So this is the assignment which we'll be discussing. Sorry. So which field in ARP? Okay. So VLAN is better than LAN. So in VLAN, we have a multiple virtual networks. So because there are some internal networks in the LAN, such as a mobile network or some internal sub networks, like we have a broader institute network, and in between we have a CSC department. So for that, we have a virtual LAN so that they can communicate or perform different operations on that virtual LAN. So that if all the time we need not to request services from the LAN. So in all VLAN, we cannot say better, but it is helpful along with the LAN. So which field in ARP packet is not filled in ARP request, but filled in ARP reply? So you know what is sent in ARP request and in ARP reply. So what is received in ARP reply? So if we just now discuss that in ARP, we have the target hardware address, which is not a content of ARP cache table. So ARP cache table does not have port number. That is true. We have timeout, we have attempt, we have protocol address. And which of the following is or are correct about RARP? Yeah, so the correct answer is B and D. RARP is often used for thin client workstation, and RARP has been replaced by DHCP. So which of the following is true about BootP? So answer is B, that BootP is only 2 second is true. BootP is a UDP IP client, not TCP. And BootP client uses port 68 while server use port 67. So which protocol is used for loop avoidance? Yeah, so the answer is C, that is STP. Then VLAN dash is used when a link needs to carry traffic for more than one VLAN. So the answer is VLAN trunking that we discussed just now. And VLAN trunking is used when a link needs to carry traffic for more than one VLAN. The next is to deal with hidden terminal and expose station problem. All implementation of 802.11 WLAN must mandatory support DCF, PCF, both are mandatory or both are optional. So we just studied that for to deal with hidden terminal problem, DCF is mandatory, PCF is optional. In PCF, the base station sends dash periodically. Yes, so the answer is C, that is beacon frame is sent periodically. So in case of hidden terminal problem, what are the cases possible? Yes, so the answer is when two stations are in the communication range, then only hidden problem is possible. So in DHCP, sorry, a client is allocated an IP address is permanently after it is switched on. True or false? Answer is B, false. DHCP does not allocate address permanently. It leases the address to for a particular duration of time. Okay, so I think it is clear. So we are done with the today's lecture. If anyone having any query, you can ask. What is PYQ? Okay, previous year question. Okay, sure. I'll upload here. Wait. TLC9P assignment 11 solutions. Okay, so you can download it from here. Okay, so I think we should end the session. Thank you all for attending the session. Thank you, you might leave. Okay, thank you.